So good morning, folks. So today, so in the last class we looked at difference and difference, design of a difference and difference estimator, and also regression discontinuity design. Right? How many of you did manage to look at that book called Effect? Yeah? It's very simply written and you also know how to do it, right? Okay? So today we'll look at one more way of dealing with endogeneity. And that method is called instrumental variables. Right? So I'll need to have the blackboard for the instrumental variables. So तो blackboard दिसेल का रे स्क्रीनवर? कॅमेरा वळवायला लागले. कॅमेरा ब्लॅकबोर्डवर करायला लागेल ना? कर ना. You can see this now? Okay. So now think of a regression model. Okay? Yeah, can you see the equation? Yeah, correct. Right. Now, suppose we have a situation where covariance xi ei is not 0, right? And that can happen because of a number of reasons. One of course is the fact that we have an omitted explanatory variable correlated with an included variable, right? Omitted explanatory var correlated with included var. Correct? The second reason could be x measured with error. Yeah? If the x variable is measured with error, you have a endogeneity. And third, y is a function of x and x is also a function of y. Right? Okay? Y is a function of x, but x is also a function of y. These are three situations where you get correlations between x and e. Right? You already know this. Let me show you why this and this happens. Right? So that we can distant है? हाँ. Okay, so we already know why omitted variable happens. But suppose now x is measured with error. Right? X is measured with error. So basically, what we have is x, which is actually x star plus vi, right? Where vi is a variable, mean zero, variance, constant variance, uncorrelated with ei, right? So suppose vi is normally distributed mean zero, variance sigma square v. Yeah? Okay? And ei and vi are not correlated. So basically, you are regressing y on alpha plus beta xi plus ei, but x is actually not the real x, but the real x measured with plus some random error. Right? So y is, for example, marks scored by your student in the final end semester exam. X is the number of hours that student has studied. You went around with a survey form and students told you they studied 3 hours a day. Somebody told you 2 hours a day. Somebody said 4 hours a day. Right? But obviously they studied 3 hours 59 minutes. They are not going to say 3 hours 59 minutes. They are going to give you an approximate number, 4 hours. In which case, x is what you have measured. Right? X star is the actual number. V is your error term. right? V is your error term. Yeah? Okay. Now, so basic U regression should have really been like this, right? You should really have xi star. But you have xi. How does xi relate with xi star? Xi minus Vi is xi star. Correct? Sure? Okay. So now, if I replace this xi here, right, what do I get? Yi is alpha plus beta xi minus Vi plus Ei. Yeah? Sure? All that I have done is just instead of this x star, I put xi minus Vi. Correct? Okay? Okay. Now, if you open this out a little bit, what will you get? If you open this out a little bit, what do you get? Right? You get Yi is alpha plus beta xi minus beta Vi plus Ei. Right? Which is the same thing as alpha plus beta xi plus Ei minus beta Vi. Right? Okay? Now this is an error term, this is an error term. So there is a new error term in your regression model, which I will call Wi. Right? So let me call Wi is Ei minus beta Vi. Correct? Sure? Because Ei is not observable, Vi is not observable. So you basically get Yi is alpha plus beta xi plus Wi. Right? What is Wi? Ei minus beta Vi. What is xi? Xi is xi star plus Ei, right? So xi and Ei are correlated. Xi and Ei are correlated, right? The original xi is xi star plus Ei, right? So xi and Ei are correlated, as you can see from here, right? Okay, Ei is included in Wi, which means Wi and xi must be correlated. So xi and the error term in this regression get correlated. So if you have errors in variables, right, you will get biased regression coefficients. Right? That bias is called the attenuation bias. Right? That bias is called the attenuation bias. Okay? Now this is a very common thing if you have, for economic data. For example, if you are regressing, say, consumption on GDP, final consumption expenditure on GDP. GDP is measured. GDP is measured with huge errors. All of us know that. Right? Okay? So that kind of a macroeconomics regression becomes a problem. If you want to find the marginal propensity to consume, for example, what are you told? C is equal to A plus BY, right? So you regress total GDP, you regress GDP on consumption expenditure, right? And you will get a beta, but that is a problem there. Yeah? Okay? Right, and in survey data, this is a big problem. If I am trying to find out the health status of children, as among many things, dependent on whether the family has household access to clean drinking water. If I ask people, what is the distance from your house to the nearest source of clean drinking water? Like if you look at, for example, the NFHS data, it will tell you how far away from the household is the source of clean drinking water there. If it's in the household, say within the household, that will say 15 minutes, 20 minutes, 25 minutes. These are recall from people, no? But 25 minutes is an approximation. The house could be 25, 7 minutes, 32 seconds, 47 nanoseconds and so on. Obviously, you don't get that in the data. Right? So when you have survey data, there is a problem. Okay? Sure? Right. So therefore, this is another issue that we need to learn to handle, right? And the third, of course, is the endogeneity, classic endogeneity, like, say, think of a market. Think of a demand curve in the market and a supply curve in the market, right? So quantity demanded is A minus quantity demanded is A minus BPI plus some error term EI, right? Okay? Quantity supplied in the market is a C plus DPI plus some error term VI, right? This is the demand curve, this is the supply curve. The demand curve is downward sloping, the supply curve is upward sloping, right? Okay. How is the price determined? But do you actually, when you go to collect data in the market, suppose you want to estimate the demand curve and the supply curve, right? Suppose you want to find the demand curve for Kolhapuri chappals and supply curve for Kolhapuri chappals. I wish somebody can do that. It's a complicated thing, right? Okay. So, what is a demand curve really? Can you tell me what's a demand curve?
It's a series of price and quantities at a point of time.
Yeah. So basically a demand curve is basically relation between what different prices, what people plan to buy at those prices, no? It's a set of plans. Supply curve is, it's a set of plans, no? What people plan to sell in the market at various prices. You can't observe plans. We don't have access to people's minds. What you can observe is only the market prices. Market prices are prices where things have been bought and sold. So those are market clearing prices. Those are equilibrium prices. At those prices, quantity supplied has to be the same as quantity demanded. You can only see the intersection points. Right? You can't see the whole market. Right? You can't see the whole demand and supply schedules. Right? Okay. Like in the market, if I say how many Kolhapuri chappals you sold, that man will say you sold 10 pairs this month. At what price did you sell? I sold them at 300 rupees per pair. I'll get this. Right? Okay. So with that, what I get is, I get quantity demanded is quantity supplied. Right? Which means A minus BPI plus EI must equal C plus DPI plus VI. Correct? Sure? Okay. So now if I take all the PI on one side, right, what do I get? I get DPI plus BPI, I put it this side, is equal to A minus C, right, plus EI minus VI, correct? Sure? So I get B plus DP is equal to A minus C plus EI minus VI, right? Or I get P is equal to A minus C upon D plus B plus EI minus VI upon D plus B, right? Sure? So P depends on EI and VI. P is correlated with EI and VI, right? This is called the reduced form. I have taken, right? PS, right? Okay, fine. So P is dependent on EI and VI. If P is dependent upon EI and VI, then obviously you see correlation between P and V here and correlation between P and E here, right? Which means that both these equations cannot be estimated independently, right? That has a name in econometrics. That is called the simultaneity bias. Yeah? That is called the simultaneity bias. Okay? Because so basically here, P is not an exogenous variable. P is determined from within the system. So P is an endogenous variable. So if one of the explanatory variables is an endogenous variable, you cannot do you can estimate these two equations independently as they are, right? You will get into a problem called simultaneity bias, right? Okay? And you get that problem many times. For example, if you are trying to understand the labor supply decisions of women from the, say, home-based, so if I am taking the labor supply decisions of household, say, helps. So I do a big survey, and of course the assumption is, as Claudia Goldin did say very clearly, that as people, as household, as incomes of women go up, right, as household incomes go up, women then tend to drop out of these labor-intensive kind of jobs, right? So you would expect the household income to be an explanatory variable. So you would say, okay, labor supply decisions, how many hours to work of a household help is your dependent variable, and the explanatory variables are the wage rate she receives and the family income, right? And the family income. Immediately you realize the family income is an endogenous variable because it's determined by how much labor supply that woman does. So immediately you have a endogeneity issue, right? So basically you need to think a lot about these equations, right? So three basic things in which you will have endogeneity issues, right? Omitted variable bias, that is, you omit an important variable that is included with an explanatory, that's correlated with an included variable. Then you have X variables measured with errors, and you have a situation where the explanatory variable is not truly exogenous, it is endogenous, right? Like in this case, for example, in the case of the gym example, right, we said that, okay, fitness levels depend upon your access to the gym. So whether how fit a student is depends upon how many times a student goes to the university provided gym, right? But there is an endogeneity, no? People who are more fit actually might be using the gym more often. Yeah? People who are more fit could actually be using the gym more often. So which means that decision to going to the gym is not an exogenous decision, it's an endogenous decision. So you can't do a regression like that. Yeah? Marks you score in economics as a function of the number of hours that you put in. But if you actually studied more in the past and you actually got more marks by studying more, then how much you study depends upon how much marks you get after studying, right? So that could actually be an endogenous variable, right? It could, for example, be the case that because you are really, if you are more studious, you choose econometrics as one of your options, right? Okay, I don't think anybody does that, but let's hope that the more studious students take econometrics as an option, right? Which means that there's already an endogeneity in the choice, no? Right? So you have a problem there, right? Okay? So because of these, can you give me some examples of these three kinds, just to make sure that you're understanding what I'm saying? Just think of this. What examples can you think of? Exports as a function of GDP growth, yes, but GDP growth also depends upon export growth, no?
That's what I example.
Yeah, so you can't really, right? You can't really do that kind of simple model. Yeah? Right? In fact, the usual macroeconomic identity that we have, yeah. Yeah, but same we will have a problem. That's what, right? Okay. Similarly, so our standard macroeconomics that we have, right? What does it say? Think of a closed macroeconomic model, right? Okay. Think of a closed macroeconomic model. Y is equal to consumption plus investment, right? Sure? Okay. C is equal to A plus BY plus EI. CI is equal to A plus BY plus EI. Right? Sure? So what do I get? I write yi is equal to A plus BYI plus EI plus investment I. Can you see the endogeneity now? Because now if I take all the y's on one side, right? So I get yi 1 minus b is equal to a plus ei plus ii. You can clearly see that y depends upon e, right? So in this equation, y and the error term are correlated automatically, right? So you can't even run a consumption function like this. C is equal to a plus by. There is always endogeneity, right? So the point is that we have to think carefully. Now there are several ways out, right? One is what people with panel data do. Okay, I'll tell you quickly the basic insight from a panel data model, right? Okay. So suppose you want to now study, say, marks scored by a student as a function of the number of lectures attended by the student, right? Okay. So yi is equal to a plus b xi plus ei, where yi, right, is equal to the marks scored by the student in a particular semester. Xi is the percentage of attendance by the student in a particular semester, and ei is the residual error term. Right? Do you see a problem with this? Why is marks? What are the determinants of marks? Studying, yes. Basic ability and aptitude for that subject, right? Look, if you put me in a music class, how many hours I practice, I'm not going to become a singer, okay? I have zero aptitude for music, right? I'm completely tone deaf, right? So it has to be, right? It has to be innate ability also, right? Sure? Okay. Now, have I included innate ability in this? Okay. So there is an omitted variable. Is that omitted variable creating a bias? It will if it is correlated with an included variable. Okay. Is that a possibility here? What is the possibility?
Having better aptitude in a subject makes you attend it more.
Yeah. If I'm really interested in singing, then I'll practice more, no? Right? Okay, if I'm not interested in singing. Yeah, I remember one kid, I was trying to impress upon that kid the need to learn sitar. Right? And he had no interest at all. Right? So I asked him, he said, why should I learn sitar? I said, of course, learn the sitar makes you a better person. He said, did you learn the sitar? I said, no. He said, why are you asking me? Right? Okay, sure. So, obviously, y is equal to a plus bi plus xi plus ei. Sure. So, omitted variable here is the aptitude. And the aptitude is correlated with the attendance. Right? But doesn't necessarily mean, right? Okay, for example, in Mumbai University, we used to have very early lectures in econometrics at 9 o'clock in the morning. And there was one student who used to stay somewhere beyond Vasai. And she was a very studious student. So she would turn up every day without fail at 9 o'clock. But that meant probably that she woke up very early. And she probably, because they were farming her, she also had to do a lot of work on her own. Right? So when she, in the class, after 15-20 minutes in class, I would realize she would start praying. I think her name was Janice or something. So one day I asked her, Janice, why, can I ask you one thing? She said, I said, I noticed that after about 15-20 minutes of class, you start praying. Why do they do that? Oh, no, sir, in our family, it's a practice to pray before we sleep, she said. She would feel sleepy, she would come, and because she would get up early morning, and natural for anyone to feel sleepy, right? And seeing all these alpha, betas, gammas makes you feel even more sleepy. So attendance, but in general you would expect attendance and this to be correlated, right? Aptitude to be correlated, the endogenitive bias. So what a panel data guy would say is that, okay, this model is actually like this, right? Where there is a constant called Ci, which gives you that individual specific aptitude, right? Okay, and say there is some coefficient, say MCi, right? Okay, sure? That's an individual specific factor, right? Because MCi is a constant, I'm just going to call it Ci, right? So they say, okay, I take this student, and we know there is a problem. I take this student, I take the marks of this student in the 4th semester and the attendance of the 4th semester. I take the marks of this student for the 2nd semester and attendance for the 2nd semester, right? So I now collect data on this individual at time period t, right? Okay, and this is constant. The aptitude doesn't change across semesters, right? And t goes from 1 to 1st semester, 2nd semester, right? If you want, it could go on to 3 and 4, right? And I is going from 1 to say 30, I have 30 students. So on the same student, for example, Revati, I take her marks in the 1st semester, marks in the 2nd semester, marks in the 3rd semester, marks in the 4th semester. I take her attendance in the 1st semester, 2nd semester, 3rd semester, 4th semester. Like Savita, I take her marks in the 1st semester, attendance in the 1st semester, so on. So I have a cross section and a time series on the same cross section, which is called panel data, right? Then what do? Think of, for example, so I have yi1 is equal to xi1 plus ei1 plus ci, right? yi2 is a plus b xi2 plus ei2 plus ci, right? So this is the 2nd semester, it's the 1st semester. Then I find the difference. So I find the difference in Revati's marks between the 2 semesters is this minus this, a will go, right? What we'll get is b xi2 minus xi1, right? Plus ei2 minus ei1. But Ci and Ci will cancel out, right? So new regression, which is looking at change between Revati's marks in the 2 semesters as a function of change in Revati's attendance between 2 semesters, will now mean that the omitted variable, which is a constant, has been removed out, right? This is also called a fixed effects regression, right? This is also called a fixed effect regression, right? Okay, so I can either do this, right? This is how a panel data model will work, right? How a panel data model will work by getting rid of the constant, unobservable constant term, right? Sure? Whereas if you think that the unobservable constant term is not a constant, but it also is a random variable, so it has a probability distribution, then you will do what is called a random effects regression, right? A random effects regression is where the unobserved variable is not a constant, it's a random variable, right? Okay, so situation could be, for example, if you are looking at a fixed classroom, right? Okay, and then if you're thinking of EI, the AI term as constant across students. Other situation could be, I have taken say 500 students at random, right? And the ability for each student could have been something else, could have been some other realization, right? In which case I have a random effects model. We're not going into that. The fixed effects model would be like this, right? Okay, the random effects model just becomes a GLS kind of a model, right? Okay. The other way to deal with it is to then say, okay, I have got these 30 students, right? I have got these 30 students. So my data for are like this. right? I've got a data which is like this. Yi, so data, marks will be like this, marks, right? Say 50, 70, 80, 20, 40, 30, right? Attendance could be, say 70%, 80%, 20%, 10%, like that, right? Then I introduce, so how many students are there? 6 students. I introduce a dummy variable, right, which is D1 for, this is 0, 0, 0, 0, 0. Then I introduce a variable called D2, which is 0, 1, 0, 0, 0, 0, like that, right? Sure? And then I do the model, then my model is, then the regression model that I do is like this. Yi is equal to beta xi, there is no constant now, plus cdi plus ei, right? Sure? Okay, and I'll get those so many different constants. For each student there will be a different intercept. And that would capture the, that is supposed to capture the ability. But that would of course unfortunately capture everything that is a fixed effect. In fact, anything when you do a difference, any attribute which is unchanging over the 2 time series will be cancelled out. For example, if you want to understand the relationship between marks and gender of a student, controlling for attendance, so if gender you think is one of the explanatory variables, right? Then once you difference the two, the gender is going to be the same everywhere in the 2 time periods. So the difference of the effect of the gender will also be eliminated. If I want to look at the income class of the student, right, whether a student comes from a particular vulnerable income category, right, or the student comes from a particularly marginalized group, then the differencing will again do away with that, right? Okay, right? So that's a problem with the fixed effects model, right? It kind of does away with unobserved variables, but it will also do away with all the other fixed things which you might actually want to, their effects you might want to estimate, right? Okay, so now that brings me on to what is called the instrumental variables, right? So what's an instrumental variable? Suppose yi is a plus b xi plus ei, and x and e are correlated, right? X and e are correlated. Sure? So basically I have a problem, covariance xi ei is not 0, right? Then the idea is I introduce a third variable called zi, which has the 2 properties, which is covariance xi zi is not equal to 0. So x is correlated with z, right? X is correlated with z, but covariance zi ei is equal to 0, right? So z is not correlated with the error term, right? Sure? Okay? So I find one variable like that. It is called an instrumental variable, right? Okay, there can be many instrumental variables. You can have multiple instrumental variables also. So for one z, suppose one endogenous explanatory variable, if you have exactly one instrumental variable, then the system is said to be exactly identified. You can think of more than one variable z, which is an instrument for a single explanatory variable. Right, you can think of z and k, which is correlated with x, and you can use both of them as instruments, in which said the system is supposed to be over-identified. Critical thing is that if you have, say, 3 endogenous variables in the regression model, like xi, there are other variables which are endogenous. You must have at least those number of instruments. Right? Okay. Now let me tell you how the instrumental estimation works. Right? First, what you do is step 1, right? Step 1, regress xi on C plus D Zi plus Vi. Find D. Find D hat and C hat. Right? This is unbiased because Vi and Zi are not correlated. Then calculate x hat I, C hat plus D hat Z hat, right? So substitute these values and find the estimated values of x hat. Right? Find the estimated values of x hat. So what do you have? You have the estimated values of x hat. And finally, in your regression now, A plus B, use x hat I plus EI. Right? Use x hat I plus EI. Right? This is called the first stage regression, x on Z. This is called the second stage regression, y on x hat I. Therefore, the method is called a two-stage least squares method. Okay, two-stage least squares method. Why is it two-stage least squares method? Because first you regress x on Z, you get the estimated values of x, and then replace them in the original regression. Why does this work? Because what is x hat? It's that part of x which is correlated with Z, and Z is not correlated with E. So it's that part of x which is not correlated with E, because it's derived from Z, no? X and Z are correlated, but Z and E are not correlated. So that part of the regression which is explained by Z, that part of x which is explained by Z, is some part which is not correlated with the error term. Right? So basically you put them here as an instrument, x hat, right? And you do this, and you hope you will get a unbiased estimate of B. Unfortunately, you don't get an unbiased estimate of B. At least in the small samples, it's not unbiased. Right? Because Z and E, X and Z, all that indirect correlation is there, no? But in large samples, as the sample size becomes large, the bias goes away and the estimator is consistent. Whereas if in the original situation where you had, omitted variable bias, the estimator was not even consistent. As the sample size increased, beta did not go close to beta. Whereas a two-stage least square, at least that property you have. Right? At least that property you have. Yeah? Sure? So this is the two-stage least square. It is used very widely. For example, there is a very famous paper by Asmaglu and Johnson on understanding relation between institutions and economic performance. Have you seen that paper? That's what gave them the Nobel Prize, right? Okay, they argued that in countries or in societies where economic institutions are more egalitarian, that is more equal, more based on more competition, right? And lead to better economic performance compared to institutions which are extractive. For example, countries like say Burundi have economic institutions which the economy is controlled by military elite, right? And they make farmers cultivate coffee, but all the coffee is bought from the farmers by the military board and sold abroad, right? That's not a competitive system, right? That's an extractive system. So the economic systems are based more on competition, more equality, right? Less extraction, more inclusiveness. Growth is faster, right? That is the kind of an argument they have. Now, if they try to do a regression of growth on institutional quality, do you see a problem? Do you see an endogeneity? Yes, because systems where economic growth is faster could probably lead to better institutions, right? So there is an endogeneity. There could be a lot of omitted variable biases there, right? Okay? So variables which are included with institutional quality and which affect growth rate, but which are not there in the regression. You see the point? So what they did was they had a very clever ruse. What they said that, okay, in general, they thought of countries in the 19th century which were colonized by Europeans. And they said, okay, some countries were very hostile in terms of climate to European settlers, right? So there, the European settlers focused on using local labor in a very extractive way. For example, the Caribbean, where slaves were imported to run the sugarcane plantations. So those were extractive institutions. Whereas places where Europeans didn't die off quickly, but where Europeans found things to be more, climate-wise more friendly, and the settler mortality was low, there wasn't much malaria, things were not very hot and all that, Europeans brought in European kind of institutions because they began to run the system. Right? New Zealand, for example, right? Or India, for example, right? Where far more European centered, so less extractive and more inclusive is what the argument was. So they use settler mortality as a thing which is correlated with the institutional quality. So they said, okay, where settler mortality was high, institutional quality would be poor because you had to drive slave labor. Whereas settler mortality was low, institutional quality could have been better. They used that, and then they showed, therefore, that's where really, have any of you read that book called do you know their famous book? Yeah, Why Nations Fail, right? That the basic argument is that you can have very extractive institutions, right? Those lead to poor economic performance, where if you have more egalitarian, more competitive, more inclusive institutions, they lead to faster economic growth. Okay, but the Chinese always like to pull the rug. So there is a political scientist called Ang Yang, right? Okay, she said that's fine, but where do the good institutions come in the first place? How do you get good institutions in the first place? It's fine. If you have good institutions, economic performance will be good. If you have slave drivers running the economy, economic performance will be bad. But what makes people, some countries have slave drivers in the first place, and so how do you get good institutions? So she has a very interesting kind of, you can look at her blog. Okay, there is what she calls complexity dynamics. She said it doesn't work like that. He said you first do some reforms, then the economy adjusts to it, right? Then there are further reforms coming from the way the economy had changed. Then the economy changes again, right? So there is a continuous to and fro process happening in a very complex way. So she says that the economy is not like a toaster, So all parts are there, and then you put in a slice of bread, and then once you push a button, the bread slice comes up. It's not like that. Parts of the economy often adjust to each other, manipulate each other, right? There is a lot of open-endedness in the way an economy evolves, right? So it's just not the button which, so the toaster might hit back at the button, right? Okay, so those kinds of things happen in economy. And that is a beautiful blog called Complexity Dynamics. Very readable. She's a political scientist, but extremely readable. She has a beautiful book called How China Overcame the Poverty Trap. So he's actually applied this to understanding China, right? It's a very nice book, but if you read her blog on complexity dynamics, I think that's something very interesting that you should know, which changes our whole causality idea very much. Because causality is still working on an exogenous variable and something, right? Effect on X to Y. But life in general is more complex. Things impact each other, and there are people on both sides, no? Y is actually some people, X is also some people doing something. Yeah, so please read that, right? Okay, so I'll now take you through. So this is what is the classic two-stage least squares regression model, right? So you basically have Y is A plus BX plus EI, X and EI are correlated because of some problem. You think of another variable Z, which is correlated with X but not correlated with E. In the first stage of regression, regress X on Z, get the estimated values of X hat, and use the estimated values instead of X in the first original regression. The regression of X on Z is called the auxiliary regression. Right? Now you do not have just one Z, you can have many Zs like that. Many variables on which you are correlated. The price for this to be paid is, because the estimate of beta hat, the variance of beta hat increases now. The two-stage least square estimator is not efficient because you got uncertainty in X hat, no? See, X hat is just an estimate. So the variance of X hat is higher than what the variance of X would have been. X is the actual number. And we know when the variance of the explanatory variable increases, right? Okay, the beta hat estimator will also become more, right? So the variance of beta hat becomes higher. So once you try to econometrics, this always happens. Once you try to solve one problem, another problem crops up. Like economics, it's a trade-off, it's a give and take. You have to know, okay, if I do this, this will become better, right? This is the kind of, will improve, but this is a new problem which will come up, so I must balance the two, right? Okay, that's really what knowing good econometrics is about. Knowing the consequences of what you do, right? And taking an informed decision. Yeah, so if your cholesterol is too high, a doctor will prescribe you statins. But statins will give you muscle ache and all those kinds of things. But a doctor will take a balance, right? If your cholesterol is too high and you are getting, the doctor said, okay, stop the statins, right? But if your cholesterol is really alarmingly high, this is okay, you know, these small pains and aches you have to live with, right? Okay, so there are side effects, right? So similarly for everything, for any medicine in econometrics, there is always a side effect, right? Sure? And therefore those things you should know. Right, now I'll take you through some exercises. See, the critical point is identifying the right instrument. Right, the instrumental variable is a good solution to end, and I think all regressions will generally be instrumental variable regressions. It's very hard to do a simple linear regression because you now seen all the problems that are there. Yeah? Okay, so I'll take you now through one example. Right? Now आपला बोर्ड गेला तरी चालेल. Theory कळली सगळ्यांनाही? It's very simple, right? But this is very important, so don't forget. Right? Okay. So now I'm sharing my screen. Okay. Did you see that book which I sent you last time, Applied Econometrics with R? हाँ, तो उसी में है. Not the small PDF, but the online. Not the Kleiber and Zeilis book. Yeah. So chapter here. Instrumental variables regression. Yeah, so this, okay, so install these two libraries, library AER and library Stargazer. What is Stargazer? Stargazer is not an econometric library. It will only produce very nicely formatted regression tables. Publication quality, because you don't want to take those and put in some word and all that, no. So this will give you Stargazer. install those two packages and do the library Stargazer. Okay. So where x, we are looking at a nonlinear regression. So basically, we are going to look at the relationship between income of schooling districts and their test scores. So there is data across districts on test scores and incomes. What do you think will be the dependent and what do you think will be the independent variable? So what do you think will be the dependent and what do you think will be the independent variable here? Is a study the relation between income and test scores of students.
The test scores is PT.
Test scores will be the dependent variables and the income will be the independent variable. Right? Sure? Okay. So now get these data and then just kind of create these variables. So basically we have size, right? So student teacher ratio, right? And then we have the average scores, and then we have income, right? And then calculate the correlation between the two. So what does the correlation say? Did you get the correlation? Can I make this bigger? Yeah? Open that book. No, you have that book on your laptops, right? No? So what is the correlation between income and scores? 0.712. So what does it mean? It means they are positively correlated. Yeah? Right? Okay. So let's first do a linear regression. Let's take the score and regress it on income. And then plot the results. Right? Okay? Plot the results. Everybody now knows how to do the regression LM, right? Dependent variable tilde independent variable will tell the computer where the data comes from. Yeah? Done? Yeah? Okay. Now add a linear line to it and then check this graph and tell me if the regression is actually fitting the data well. From what do you think? Is a linear regression a good fit? Yeah? So you see that there is whole bunch here, no? So probably this line should go like this, curve around like this. Yeah? So test scores depend upon district income but in a non-linear way. As people's incomes improve, their test scores improve, but as incomes improve a lot, test scores don't improve that much. Right? If you're poor and if your income increases a little bit, your test scores increase a lot. But if you're rich, already rich, then just a small increase in your income doesn't increase your test scores so much. आ गया सबका? Okay. तो ये नहीं आता है, right? So we need a quadratic regression at all, right? So you have to read a square term for income. So now run this regression. Income square, right? Right, now you see there is something called Vikov HC, right, in this. What is that Vikov HC? The Vikov HC, so there is something called heteroskedasticity. What is heteroskedasticity? The error terms across regulations are not independent, they are correlated with each other. If they are correlated with each other, then sigma square E upon summation xi square doesn't become the right formula. That formula has to be adjusted. Right? So what the Vikov does is, it actually adjusts that standard errors. So these are called heteroskedastic consistent standard errors. So HC stands for heteroskedastic consistent. And there are various ways of correcting it. HC1, HC2, HC3, HC4, etc. So you put it at HC1. Right? Sigma square upon summation xi square is the formula for variance of the error, the variance of the estimator when the error terms are not correlated. When the error terms are correlated, that formula has to be modified. Right? That formula has to be modified, has to be made consistent with heteroskedasticity. There are ways of making that, HC1, HC2, HC, different ways of modifying that. Right? So HC1 is one of those formulae. Right? Heteroskedastic consistent standard errors. Right? Yeah? And you get this regression now? Somebody wants to join? Okay. Yeah? Right? So basically, a coef test, so call this model the quadratic model. Yeah? Hey Alef, have you got this? Okay, what does the coef test tell you? So basically the coef test is telling you that these are the T. Now suppose if you didn't do this, right, if you just said coef test quadratic model, if you didn't put Vikov dot is equal to, right, see what you get and compare the two T values. Just run a regression, just say coef test quadratic model without saying what the V curves are. क्या आ गया? Standard errors are different, right? Standard errors are more? Okay. So when you actually adjust, because as you know, if there is heteroscedasticity, the standard errors, the coefficients are not efficient. So you need to correct for that, right? And so HC1 VCOV will correct for heteroscedasticity. So one way of correcting for heteroscedasticity. Okay, so once you do this, okay, so this is your estimated regression. Okay. And as you know, you can look at this and then you'll see that it fits well. Right? Seems to be a better fit, no? The quadratic line seems to be a better fit, right? Okay. Okay, my God. Now, okay, think of IV estimator. So this is okay. This is something that we got. Now suppose we are doing an IV estimator, right? So the two conditions that we have is Z and X should be correlated. Rho Xi Zi means correlation between X and Zi, which is called instrument relevance condition. Yeah? And then Z and the error term should be uncorrelated, which is called instrument exogeneity condition. That's our two conditions that must be satisfied for instrumental variable regression. Instrument relevance condition, which is that X and Z must be correlated for Z to be a relevant instrument, and instrument exogeneity condition, that is correlation between Z and the error term must be 0, right? Hey, someone wants to join this call. Yeah? Okay. So now we have so basically what we have is Xi is regressed on Zi, right? Sure? And then we have basically Zi, so that we don't need to worry about. Now here, right, we're going to study a relationship related to demand for and the price of commodities, simple but widespread problem in economics. Health economics is concerned with the study of how health affecting behavior of individuals is influenced by healthcare system and regulation policy. Probably the most prominent example in public policy debates is smoking as related to many illnesses and negative externalities. Right? It's possible that cigarette consumption can be reduced by taxing cigarettes more heavily. Right? Apart from scaring people with all those scary pictures, the horrible pictures to look at, no? Yeah? And before any film also they show all that. Right? It's horrible. I mean, I just close my eyes when that.
But there is another behavioral observation. People think that the product they are buying that is potent because of those pictures. They ask specifically, oh, cancer wala. But there is another behavioral observation. People think that the product they are buying that is potent because of those pictures. They ask specifically, oh, cancer wala.
Ah.
So, what is the difference between potent and cancer wala?
People are people, Baba. Okay, the question is by how much taxes must be increased to reach a certain reduction in cigarette consumption? How much taxes should you increase, right? Okay. Economists use elasticities to answer that kind of a question, right? Okay. So what we are going to do at is, look at this data, cigarettes SW. Right, so this package called, library called cigarettes, library AR, data cigarettes SW. Yeah? Yeah, so have you taken the data, library AR, data cigarettes SW. Okay. Now we're going to do a relationship between the log of the quantity of cigarettes smoked, beta 0 plus beta 1 log of the price of cigarettes. Price per pack, right? So basically QI is the number of cigarette packs per capita sold and PI is the after-tax average real price per pack in state I. So we have a cross section. Yeah? So the demand function is log of QI per capita sale of cigarettes, right, as a dependent variable, and the average price per pack, after tax average real price per pack of cigarettes in state I, right? Okay, now you see a problem there? We are trying to do a demand function, no? We are looking at how much if you increase prices, how much is the demand for cigarettes fall. But we just learned that you can't do that like that. P is correlated with endogenous, there is endogeneity in that. Right? Sure? Okay? So, we need to think of an instrument. Okay, so now we use sales tax as an instrument. What is sales tax? The sales tax variable here is, okay, the proportion of taxes on cigarettes arising from the general sales tax. So the general sales tax and the proportion of that sales tax which comes from selling cigarettes across different districts. Now the point is that this would be correlated with the price of cigarettes. Yeah? This correlates with the price of cigarettes. But this does not affect quantity of cigarettes directly. It only affects it through the price of cigarettes. Right? So therefore it would be uncorrelated with the error term. Right? Sales tax is so we have data on quantity sold of cigarettes across different districts, price of cigarettes across different districts. We want to find out the price elasticity of demand, right? We want to know if price increases, what the percentage decline in cigarette sales. But we can't do a simple linear regression because as we know there is endogeneity, right? Price and quantity are determined simultaneously. Right? So price is an endogenous variable. So if endogeneity variable, there is simultaneity bias. Correct? So what do? We think of an instrument. So these guys say that one possible instrument is so every state collects sales tax, out of which some proportion has come, some portion has come from selling cigarettes. Right? The proportion of sales tax revenue for any particular district that's come from selling cigarettes is correlated with the price of cigarettes in that district. Right? But is not an independent source of the demand for cigarettes. It will only affect the demand for cigarettes through prices. Right? So, it's a valid instrument because it's correlated with the price of cigarettes, but is not correlated with the error term in the original regression, which has to do with the demand for cigarettes. Right? But this variable does not affect the demand for cigarettes on its own. Right? It only affects it through the price of cigarettes. So it's a valid instrument, right? So now what we do is, we basically find cigarettes price is cigarettes divided by, so this is basically the real price, right? This is how we calculate the sales tax. Cigarette price there is correlation. So you want to do it for one particular year, right? Year 1995. Okay? The first stage regulation, price of cigarettes, X, is regressed on the instrument Z, sales tax. Right? And then in the second stage, so this is the first stage regression. So do the first stage regression. You just click here and copy paste, no? It's an easy job. Yeah? So do this and tell me what happens. The first stage regression, you get this first stage regression? Yeah? And calculate the R square. ये आ गया फर्स्ट स्टेज रिग्रेशन सबका, राइट? हेटेरोस्केलेसिटी कंसिस्टेंट वेरिएंस कोवेरिएंस मैट्रिसेस HC1. Okay, so first stage regression, everybody's got this. Look at the R square of the first stage regression. .47. Yeah? Right? Okay. Now get the predicted values, so fitted values, no, y hat, which can be done like this. LCPIG understroke pred, you give it whatever name. The model is called CIG S1, right? The first stage model, CIG S1. And then you take the adjusted R square, right? Okay. Now in the second regression, the demand is the sale for packs, regression on LCIG P pred, right? So this is the kind of model you get, which is the two-stage least squares model. R will of course automatically do this through a command called ivreg. You don't have to do the two regressions, right? R will do it on its own. Everybody got this? First, second stage regression, yeah? Okay, then this command called ivreg. Okay, ivreg. So basically what you do, CV ivreg, the regression not the model, command is not LM, the command is ivreg, dependent variable is log packs, independent R price, and then you say sales tax is the instrument, right? Sales tax is the instrument. So what do? You write the regression equation, y is equal to A, so y tilde x slash, okay, and then the z variable. And as you can see, you get the same, right? Are you getting the same results? Yeah. Again, the variance covariance matrices, you have to be careful. Okay. Now the thing is, this is an important point, right? We have demonstrated that running the individual regression for each stage of TSLS using LM leads to the same coefficient estimate as when using ivreg. But the standard errors reported for the second stage regression are invalid because they do not account for the use of predictions from the first stage regression. When you did the second stage regression, you put x hat. But the computer just calculated the errors as if that was x. But of course there is a problem in that, right? So you have to do a x hat, and that is what the ivreg command does. It adjusts for the, so basically if you look at the coefficients, the t value for the log price is minus 3.397 here, right? Whereas in the second regression it was minus 3.0469. In the second regression, second stage regression, the t value for LCI GP understroke pred was minus 3.0469. It is a minus 3.3977. This is corrected for the fact that x hat is a predicted variable, right? Okay. Yeah. And the essential point is that if you have three endogenous variables in the regression, for each endogenous variable you require one instrument. Because you need to have, so if there are x1 and x2 are independent variables and both x1 and x2 are endogenous, you require z1 and z2. You require a z1 which is correlated with x1 but not correlated with the errors. You require z2 which is correlated with x2 but not correlated with the error terms. Right? You can have z3 also. You can have two endogenous variables, two or more instrumental variables. But you must have at least two. Right? Otherwise your model will be under-identified. If you have the same number of instruments as the number of endogenous variables, you have an exactly identified model. If you have a lot of instruments for just two explanatory endogenous variables, there are three instruments, then you will have an over-identified model, which is okay, right? But you should never have an under-identified model because the regression will not happen, right? Otherwise, the basic principle remains the same. You write IV reg, you say what are the endogenous variables, and then you write for those many instruments. So the command for IV reg, for example, here, right, will be like this. So all exogenous variables are instruments as well, right? So if you can actually see this, this is, and the same conditions will apply, but in a more general form, right? So if you actually run through this, you will be able to do this on your own. Now I think you've got the basic idea. You've got this book also, and you can copy, paste and do this. Sure? Okay? Right. So that brings us to the end of all these 13 weeks now. Right? 12 and a half weeks really, because today we only did half a lecture, right? Okay. So do you have any questions on what we did? So we started by learning basic data cleaning, basic R. We learned data visualizing in R. We learned handling fairly large data sets, cleaning data sets in R. Then we learned basic things like T, F, chi-square, Z. We learned the basic linear regression model, right? Okay, also the multiple linear regression model. And then we learned about instrumental variables. We learnt about some basic things about policy evaluation, difference and difference estimators and regression discontinuity designs, right? Now, the whole objective was to give you some start. You have all these books now, right? This book is there, the AER book is there, Applied Econometrics with R book is there, right? These are all easily downloadable, right? And also there is a lot of online things that you can learn, right? Sure? So the idea was to actually make you feel a little bit more comfortable in using R, doing econometrics, being able to kind of start running some regressions and so on. I can't teach you the whole of econometrics in this kind of a thing, right? Okay, so hopefully this has been useful to you, yeah? And you can of course get back to me whenever you want to on any questions that you might have and so on. You'll all, at least those who have attended the mandatory number of lectures, will get the certificates from Indian Econometric Society, right? Okay, which Savita will help you facilitate, yeah? And that's it really. Sure? And we must also thank the ISLE for giving us the infrastructure. All the lectures will be uploaded, remaining lectures will be uploaded a couple of days once we get all of them. If anybody wants to collaborate on some research projects, etc., then please let me know. Very large scale, very granular data cleaning exercises, but which feed into fairly complicated econometrics. So if anybody is interested, let Savita know. We'll figure out something in which you can kind of join with a very large research project, which is with very granular data sets and geography and space and that kind of a thing. So you should let Savita know. And so, thank you very much, folks. Right. I'll send that tomorrow morning, Revati. Sure. So please join us for tea. Thank you everybody, online folks also.